Hello friends, we are going to solve two examples on moments of a force. The first example, a uniform rod of length 1 meter weighing 100 Newton is supported by two knife edges A and B placed at 10 centimeters from its edges. What will be the reactions at the supports when a 40 Newton weight is suspended 10 centimeters from the midpoint of the rod? So, to solve this question, we'll start by drawing a diagram. So we have our uniform rod of length 1 meter weighing 100 Newton. That means that from the center of the rod, there's a weight of 100 Newton pointing downwards. Now, if the rod is 1 meter, then from the center to one end is going to be what? 1 meter, that's 100 centimeters divided by 2. So that will be what? 50 centimeters and then 50 centimeters. Good. Now we are told that it is supported by two knife edges A and B. These are the pivots. Placed 10 centimeters from its edges. So we are going to have our knife edge A over here, and then another knife edge B over here. And we are told they are placed 10 centimeters from the edge of the rod. Now, once there's a pivot, it will have a normal reaction, RA, and another one, RB, perpendicular to the rod. Very good. What would be the reactions at the supports when a 14 Newton weight is suspended 10 centimeters from the midpoint of the rod? So if this is the midpoint of the rod, 10 centimeters from the midpoint of the rod, we have a 40 Newton weight. So maybe we can call this a point D. Maybe this center point, we can call it C. So we have labeled all our points. Now CD is 10 centimeters. Okay. And they are saying that what will be the reactions at the support? So we are looking for RA, we are looking for RB. Now there's a clue that this thing is in equilibrium because they are saying that a uniform rod of length is supported. Now, once in equilibrium, we have two conditions. The first condition is that the total upward force is equal to the total downward force. We will use this to get our first equation. What are the total upward forces? We have our reaction at A, RA, and then our reaction at B. And what are the total downward force? We have the weight of 100 Newton plus the weight of that body, okay, 40 Newton. So we can say that therefore RA plus RB will be 140, and that will be our equation 1. Now the second condition for equilibrium in moments of force is that the total clockwise moment should be equal to the total anti-clockwise moment. Okay, so we are going to sum the clockwise moment, and then we'll sum the anti-clockwise moment, and then we will equate them, and that will help us to find the reactions that we are looking for. So let's consider our diagram. We want to look at the clockwise moments. You either take one of the pivots. You can decide to take the pivot at A or to take the pivot at B. Okay, so let's take the pivot at A. Let's taking the pivot. After that, we can take the pivot at B as well, but let's start with the pivot at A. So when we take the pivot at A, now we are going to now try and point our forces towards A. Now, if the force moves from right to left, let me just try and draw something like this. If the force moves from right to left, what would that be? Yes, that would be a clockwise movement. But if the force moves from left to right, that would be what? An anti-clockwise movement. So clockwise is from right to left, moving in this direction. Anti-clockwise is from, let me draw the anti-clockwise properly, just a minute. So clockwise, if this is our clock, we have 12 o'clock, we have 1 o'clock. Clockwise movement, we are moving from right to left. Now the same clock, we have 12 o'clock, we have 1 o'clock. Anti-clockwise movement is from left to what? Right to left, left to right. Okay, I hope that is clear. Good. All right, so let's continue. Let's take clockwise movement. So if we want to look at the forces from A, we have the weight. It is moving from left to right. It will be clockwise. Okay. Then what about the 40 Newton? Also in that same direction, it will also be clockwise. But then if we consider RB will be moving from right towards the left, and that will be anti-clockwise. So we'll have a C here, we'll have a C here, and then we'll have an A over here. So let's go ahead. So we want to take the two clockwise moments. You know that moment is given by FD, the force times the perpendicular distance. So what is the force? The first force is the W, 100 Newton, times what would be the perpendicular distance from the center C to the pivot E. Now we know that from this end point to C is 50 centimeters. If we take away 10, we should be left with what? 40 centimeters. So we have 100 times 40. Now let's look for another clockwise moment. This is the second one. Yes, we have a force of 40. And what would be our perpendicular distance? We have 10 plus 40, giving us what? 50. So if we multiply, we should have 400 plus, 4,000, 4,000 plus 2,000. And this should give us 6,000 Newton meter. And that is our clockwise moment. Now let's look for the anti-clockwise moment. Using the same formula FD, in this case, our F is RB, the reaction at B. We don't know it. What is our perpendicular distance? So we are moving from this reaction all the way to the point A. Let's look for the distance. Now, from D to the end point is 50. So if we take away the 10, this should be what? 40 centimeters. So we have 40 plus 10 giving us 50 plus another 40. 40 plus 10 giving us 50 plus another 40. No, let's hold on a second. Let's look at this. This should not be 40. It should actually be 30 because we took away 10 from this end and 10 from this end. So we should be left with 30. Yes, let's take note of that. So the 30 plus 10 plus 40, that should be 80. 80. So our anti-clockwise movement will be 80 RB. Okay. So in equilibrium, we are saying that anti-clockwise movement should be equal to the clockwise moment. We have already established it here, that the sum of the clockwise movement should be equal to the sum of the anti-clockwise movement. Let me put sum here so we don't get this confused. So we already established that our clockwise movement is 6,000 and our anti-clockwise movement is 80 RB. So to find RB, we'll divide both sides by 680 and we should get our RB to be 6,000 divided by 80. That should be 75 Newton. Now going back to our equation 1 over here, we can find our RA, because RA plus RB should give us 140. So RA minus 75 will give us 65 Newton. So we can conclude that therefore our reaction at A is 65 Newton and then our reaction at B is 75 Newton. All right. So how about if we want to work with the pivot at B? How about if we want to work with the pivot at B? We've already established our equation 1. Yes, we are going to use that. But then now our clockwise movement and anti-clockwise movement will change. So if we look at B, then we are going to consider the weight and then the weight of 100 Newton and then the object of 40 Newton. Now these two will be clockwise moments. So we will have the weight of 40 times the perpendicular distance from C to the point B. That will be what? 40. So we are going to have 100 Newton times 40, that's the perpendicular distance, 100 Newton times 40, plus 40 times 30, 40 Newton, that's the weight, times 30, that is the perpendicular distance from G to the point B. And this should be equal to RA times what is the length all the way to RB? 40 plus 10 plus 30, that is what? 80. So if we sum this up, this should be 4,000 plus 12,200, and this should give us 80 RA. So we'll have 5,200 over 80. 5,200 over 80 should be RA. So what would RA be? If you divide, you will get 65 Newton. Applying that in your equation 1, you will find RB to be also what? 75 Newton. So we are getting the same thing, whether we use the pivot at A or the pivot at B. All right. Let's look at the second example. A uniform rod, APC, 10 centimeters long, of mass 15 kilograms, is supported in a horizontal position. This tells us it's in equilibrium. On a knife pivot at the point P. If masses 20 kilograms and 25 kilograms are supported from its edges A and C respectively, calculate the magnitude of the reaction at P and then calculate the distance AP to 3 decimal places. All right. So we'll start by drawing again. We have our horizontal rod, uniform rod, APC, and it is 10 centimeters. It has a mass of 15 kilograms. Now, since they gave us mass, we will find the weight. We are given G to be 10 meters per second. We know that W is equal to mg. So in this case, we have our mass of 15 times our acceleration due to gravity, 10. And this should be 150 Newton, right at the center of the rod. So let's call this B. Let's call this A, B, C. And B is the center. Now, we are told that it's supported on a knife pivot at a point P. We are not told where P is. P could be before or P could be after the center point. Let's assume perhaps that the pivot P is after. It's just an assumption. Good. Now, since APC is 10 centimeters, from the point AB should be 10 divided by 2, 5 centimeters, and then a BC should also be 5 centimeters. Now, let's call BP X centimeters because we don't know. Now we are told that masses of 20 and 25 kilograms are supported from the end. So if it's a mass, then it will give us weight. Weight is equal to mass times acceleration due to gravity. So we are going to have a mass here, 20 times 10, giving us 200 Newton. And then another one here, 25 times 10, also giving us what? 250 Newton. So we are looking for the reaction at P. That's the first thing we are looking for. And the second thing is we are looking for the distance AP. The distance AP. Now we can see clearly our diagram. Very nice. So since our uniform rod is in equilibrium, our first condition will apply, which is that the total upward force will be equal to the total downward force. So the upward force, we have only one. That's our reaction at P. And for our downward forces, we have 200, 150, and 250. Let's sum them. 200 plus 150 plus 250. If you check this, we should have 200 plus 150, 350, 350, 600. So we should have 600 newtons. And that is the reaction at P. So we've solved the first part of this question. Let's look at the second part. We are to find the distance AP. That's the second part of this question. AP. Now from our diagram, we can see that AP is 5 plus X. Now someone will say, why didn't you bring it here? Now if AP was actually located here, that would be fine. And then X will be negative, so it will end up being 5 minus X. So not to worry at all. Wherever you put it, it's just an assumption. Now, once we find X, we should be able to find our AP. So let's use the second condition, which is that the sum of clockwise movements should be equal to the sum of what? Anti-clockwise movements. Now, we have only one pivot, which is at P. So let's look at our clockwise movements to begin with. Clockwise, we are moving from what? Right to left. There's only one clockwise movement, and we can see that that is 250 times whatever perpendicular distance there is here. Now, we know that from B to C is 5 centimeters. So if we take away X, then PC will be 5 minus X centimeters. So that's our perpendicular distance times our 200. So our clockwise movement is going to be 250, times our perpendicular distance, 5 minus X. Now what about the sum of anti-clockwise movements? Anti-clockwise movements. We have first this weight, 150 times X, that's the perpendicular distance, plus another one, 200 times 5 plus X. So we're going to equate them and then find X. So 250 into brackets 5 minus X is equal to 150X plus 200 into brackets 5 plus X. Let's expand. 250 times 5 is 1,250 minus 250X is equal to 150X plus 200 times 5 is 1,000 plus 200X. So now let's group like terms. We should have 1,250 minus 1,000 should be equal to 150x plus 200x plus 250x. So 150 minus 1,000 should give us 1,250 minus 1,000 should give us 250. And if we sum these three, we should have 600x. Let's divide both sides by 600 to find x. And our x is 0.4167 centimeters. So what is AP? We have established that AP is 5 plus x. Now x is positive, so it tells us that yes, P was to the right of the midpoint. But if you put it on the left, you would get a negative answer, and then you just have to subtract. That is not a problem at all. So we have 0.4167 plus 5. And this should give us 5.4167 centimeters. We were told, let's go back to our question. We were told to correct it to 3 decimal places. So let's look at it. We have 1, 2, 3. This should be approximately 5.417 centimeters. And this is our solution. Try your hands on this and some other problems, and